I'll begin with a word of prayer. Heavenly Father, we thank you for this day and for this classroom. Pray that it continue to be unoccupied. And just thank you for helping us to see this reschedule of time, and hope that it'll be productive for everybody here, and that we'll just learn some more things about this this math we're looking at, Lord. In your name I pray. Amen. So at the moment, I'm just trying to essentially work through this paper, which collects my thoughts on this topic of calculus over the past few years. And I mean, roughly speaking, what this paper is about is trying to bring the works of Ward and Wagner, who wrote these foundational papers in this topic in the 40s. Basically, again, the topic is just what happens to calculus when we replace the real numbers with an algebra. And what we did yesterday is we talked about what's the definition of an algebra, what's the regular representation, and we actually calculated the matrix regular representation for like the complex, the hyperbolic numbers cross the complex numbers. You guys should, like, watch it at double speed. You'll get what you need pretty fast. I don't want to save it there. Come on, don't be so dumb. Where am I? Hey. All right, so I'll save the history for some other day. So just to try to get us up to where we were briefly. First of all, I defined an algebra, right? Said it's a real vector space of an n-dimensional real vector space, and it has a bilinear multiplication. It's associative. It's unital. I say its elements are A numbers, except that I almost never say that. But people do say that, like it's a complex number, it's a hyperbolic number, right? But if we have that xy is equal to yx for all things, it's a commutative algebra. We talked about left and right multiplication maps. We noticed that if they commute, that means that that is equivalent to assuming associativity of the algebra. We observed that every right alinear map could be written as a left multiplication by an algebra element, right? And so there's an isomorphism between the set of right alinear maps, or there's an isomorphism between the left multiplications of the algebra and the algebra itself. And the isomorphism we wrote down explicitly last time, and I proved that it changes the multiplication of the algebra to composition of the endomorphisms of the over the algebra. Here's proof that the sum of the linear combination of right linear maps is again right linear. It's proof of it right there. I didn't write that out last time. There's the proof. And down here, I did this in class last time. Here's the, well, this actually proves that the composition of right linear maps is right linear. I don't think I even did it last time. Yeah. So there's a proof that this R sub A, the so-called regular representation, forms an algebra with respect to the composition of operators, and in fact, it's isomorphic to the given algebra we're looking at. So that gives us a way of studying A. Then if we pick a basis for the algebra, remember the algebra is an n-dimensional vector space, so we can pick a basis in terms of linear algebra, and we can look at the matrix of these right linear maps, maps in the regular representation, and the matrix is what we'd call the matrix regular representation. I've been trying to get in the habit of adding the word matrix here when I talk about it, just to have a different, like, people will say the regular representation is either the endomorphisms or the matrices, and like, but it's probably helpful to students for me to say matrix regular representation when I'm talking about a matrix versus just regular representation when I'm talking about a transformation. Of course, most important case would be when we have the case that the algebra is identified with Rn as a point set, and in that case we can just look at the standard matrix, right? And that will give us the regular. You notice I don't need the basis dependence here because we use the E1, E2, En usual standard basis in that context. This is a tiny subspace of the set of all matrices. It's an n-dimensional subspace of an n-squared dimensional vector space, you know? So these kinds of matrices are really quite special. Like I point out here, a little bit more nuance. Any choice of beta, this is actually a subalgebra. It's not the same. If you choose a different basis, you get a different subalgebra. But they're related in a very natural way. They're related by conjugation. If you do a change of basis from one basis to another, then there's a unique similarity transformation which connects any two of those. This is my next theorem, that if we pick different bases, then that matrix regular representation and that matrix regular representation of the algebra, they're related by conjugation. There's an inner automorphism of GLA which maps one to the other. And here's, oh man, I really want that to be equals. I'm still coming to terms with. There's the LaTeX is CONG, I think, /CONG. This is like sim equal or something. I don't know. It's not the one I want. I want it to be equals. You know, whatever. Anyway, these are isomorphic. All right. Here's the explicit isomorphism. Let's see here. Most important, basically, is the idea that if you want to go from A to RA, how do we do that? We map the algebra element alpha to just multiplication by alpha. That's the isomorphism. If you want to go the other way, if you want to start with a right linear map and get, you know, what is it, the left multiplication by, it's just whatever value the map takes at the identity. Anyway, I did that last time. I should go on. All right, so we actually calculated so sometimes I think that maybe I should use this notation like a number map. We take in the regular representation, we spit out an algebra element. How do we get the number? What's the number corresponding to the regular representation t? It's just t of 1. That's the algebra element which corresponds to it. Or the number corresponding to a matrix regular representation would be the oh, it's still t of 1, but so I'm kind of overloading this hashtag. Oh, I'm sorry, this number symbol. As I've already put it out down here, this is not a hashtag. That footnote has disappeared in my journal submission version of this for some reason. I'm starting to think that people who review articles for journals don't have a very good sense of humor. Sometimes. I don't know. But, okay, where was I? Theorem, if we have a basis for an algebra and that's the identity in the algebra, then the matrix which represents X is just that, all right? I mean, it's almost just the definition, really. I think that is so this theorem became a definition last class, didn't it? I wrote that down as the definition, didn't I? So what I consider as foundational here, I think this is why I should have had the paper printed out to give like last class I was just trying to go off the top of my head, and as you can see I forgot where I anchor things, so my definition became a theorem and vice versa. Oops. Anyway, however, wherever you start this vicious circle of ideas, does everybody understand these things so far? No? You're good, King? Yeah. All right. Moving along, we have units. We have zero divisors. You can talk about the group of units. I use A upper X for that. Zero divisor, use ZDA. There doesn't seem to be a very universal notation for zero divisors. I asked on the stack for if there's like is there a standard notation? No one really seems to think so. So I figure this is as good a notation as any zero divisors of A. X equals to 0, or X is a zero divisor in the usual sense of zero divisor. you could just say that there exists y non-zero such that x times y equals to 0. That would throw in 0 just the same. Anyway.
I think y zero divisor a is not equal to 0, but in the set y zero divisor x can equal 0.
Well, what I'm saying is this ZA, the zero divisors of A, it includes both 0 and the sort of non-trivial zero divisors.
Okay. Okay, I see,
Yeah. It's much the same situation like when we talk about eigenspaces in linear algebra.
Yeah.
The eigenspace, it's full of eigenvectors, right? Except the one that's not,
Yeah.
0. So it's just like that. Isomorphism transfers units, zero divisors. So if we have isomorphic algebras, then 1 goes to 1, inverses map to inverses, zero divisors map to zero divisors. These things we can all prove. That's actually very, very useful. Because we have an isomorphism to matrices, and for matrices we have determinants. So, if I have the regular representation of A and a basis beta, then that's either 0, a unit, or a zero divisor. It's what's called a classical ring. Classical rings have a trichotomy. The elements in the classical ring are either 0, a zero divisor, or a unit. For example, Zn, any Z modulo n is a classical ring. There are rings which aren't like this. But apparently, those rings are not finite dimensional real associative algebras. Right? Okay, so in fact, we know more. We actually have straight up a formula for the inverse of a matrix. Right? It's 1 over the determinant, the transpose of the adjoint. Right? Actually, people don't call this the adjoint anymore. They call it the adjugate. Because adjoint has another meaning in abstract linear algebra. So that terminology, I think, as I look at the more modern linear algebra books, it seems like everybody's calling it the adjugate or something. Or classical adjoint. Yeah, also that. Yeah, I am guilty of saying that as well. Anyway, none of these things are especially hard to prove. This argument you might find interesting. If the determinant is 0, right, that means that there's a constant term in the minimal polynomial. Then the constant term in the minimal polynomial is 0, right? If the determinant is 0, that means that 0 is an eigenvalue, which means that when you look at the minimal polynomial, it's got m of t has to have a t minus 0 term in the factorization, which is to say that you can factor t out, which is to say that there is no constant term except for 0, right? So that means that the minimal polynomial has the form t to the k plus da 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 plus c1t, right? And then we know from the theory of polynomials in linear algebra and the Cayley-Hamilton theorem, for example, that that discussion, one of the things we learn is that if you evaluate the minimal polynomial at the matrix, what do you get? You get 0, right? I mean, that's why it's called, that's essentially, I'm just telling you the definition of the minimal polynomial, right? It's the smallest monic polynomial, which when you plug in A in this sense, you get back to 0 matrix, right? So I know we don't spend an awful lot of time on that in linear algebra here because, it's introductory linear, but in this current context, since there's a common factor of t everywhere, that means you can factor A out, right? And so that means that A times this is 0, which means that B equals to that is a zero divisor in the matrix, right? So there you go. There's an explicit constructive, if you will, in some sense, demonstration that if the determinant is 0, it is a zero divisor. There are other ways of constructing a matrix which multiplies the given matrix to get 0. You can do things like use the theorem that if the determinant is 0, there has to be a non-trivial solution. to the homogeneous problem, and you can use that non-trivial solution to construct this matrix B such that A times B is 0. And I think if you look at the proof in that book we were looking at, King, by what's that? Yeah, matrix over commutative ring. I think if you look at McCoy's theorem, that's about, it's more or less based on that kind of argumentation. I'm getting off track. Okay, so anyway, long story short, in the algebra, we either are looking at 0, a unit, or a 0 divisor. That's it. One of the interesting things about 0 divisors is what? Well, ZA, I mean, the 0 divisors of A, well, that's the solution set to the determinant of an arbitrary regular representation being 0, right? So that's an n squared nth order polynomial equal to 0, right? And trying to think about how to say this. Well, the set, this is the solution set of determinant A equals to 0, right? I mean, it's an nth order polynomial equation in the components of A, which includes A equal to 0 and at most an n minus 1 dimensional space of 0 divisors. How do I know that? How do I know that the space of 0 divisors can't be n dimensional? Yeah, it'd be the. Yeah, I think it would force the unit to be a 0 divisor. Now, I'm not sure I know of. Well, actually, no. The hyperbolic numbers are 2-dimensional. The 0 divisors are the pair of lines, right? Y equals x, y equals minus x. We worked that out last time. So that's 1-dimensional. I mean, it can be. In fact, it can be n minus 1-dimensional. I don't know if it always is. I'm not sure. How big? Is it always codimension? Like, is this set of 0 divisors always n minus 1-dimensional? As I think about it, it can be. I mean, if you look at the 3 hyperbolic numbers, there's a plane of 0 divisors, and there's a line of 0 divisors perpendicular to that plane. So you both have a 2-dimensional 0 divisor piece and a 1-dimensional 0 divisor piece. The set of 0 divisors doesn't have to be a manifold. It has different pieces with different dimensions, right? I mean, it's some sort of union of linear data. And part of the reason you can see that is that the set of 0 divisors is fixed under negation. If you have x as a 0 divisor, then, well, minus x is also a 0 divisor, right? So whatever is your set of 0 divisors, it has to be stuff that's symmetric about the origin, right? So if it can't be a ray, it's got to be a line. It can't be half a plane, it's got to be a whole plane. What else could it be? I don't have a good sense of that yet. What are possible 0 divisors? I mean, what can 0 divisors look like generally? For uglier choices of basis and stuff, I have no general sense of that yet. I'm just cautious. This theorem is kind of important to some later stuff. The n-dimensional real associative, there exists an invertible basis, all right? So because the 0 divisors are at most n minus 1 dimensional, that means if you were so unfortunate as to pick a basis which had a 0 divisor in it, all you got to do is just perturb it ever so slightly, and then you're to a unit. And you just have to be careful not to perturb it so slightly, perturb it so much as to create a linear dependence between what already exists. And if you sort through this, it's clear that there should be an invertible basis. Well, the thing is, the units are dense in the sense of real analysis. I mean, what does it mean for a set to be dense? The rational numbers, for example, are dense in the reals. What does that mean? Something to do with Cauchy?
I mean closure.
Closure, right? Pick a number, there's always an infinite number between two numbers. Yeah, I think if we take, this is what I'm remembering, and you can correct me if I'm wrong later, but if we pick a point and we look at an open set around that point, there will be infinitely many elements from the dense set in that set.
Dense set is the one where the closure is the whole space.
Dense set is the closure is the whole space. That sounds right. So for the hyperbolic numbers, you know, here's the zero divisors, right? So if you pick any point, of course, if you pick a point out here, pick any open set, you know, you can use the usual. We're using Euclidean topology, so the open sets are open disks. Everything's a unit in there, yay. The only interesting points are like these ones, right? But if you take an open set, remember, it's not open with respect to the relative topology of the line. It's open in the sense of the hyperbolic plane. And so, yeah, I mean, like, of course, these are all units. Anywhere except for those two lines are units. And for the three hyperbolics, if you just think about open balls, whether you pick the normal line of zero divisors or the normal plane of zero divisors, either way, you've got units. So, yeah, the units are dense. I'm sure you could, there's doubtless a nice like topological argument based on the continuity of the determinant and the fact that the set of units is the inverse image of whatever it is, you know, and so forth. But let me not get off into that stuff. All right. Examples. Now, this is actually why I have this out. So sorry about the review, a necessary evil of having, you know, half the class their last class, but you'll forgive me. So what are examples of algebras? Real numbers, stupid case, algebra. One-dimensional, obviously. Complex numbers, algebra, with the usual complex multiplication. In fact, it's a field because every non-zero element has a multiplicative inverse, as you guys know. The matrix representation is exactly this, right? To get the second column from the first, we look at a plus ib times I. So here we're using the basis that 1 is equal to E1 and I is equal to E2. We're identifying the standard basis with 1 and I when we write this. Hyperbolic numbers, you know, r plus the direct sum of r plus jr, where j squared is 1. So typical hyperbolic number, a plus jb. And so when we multiply them, it looks like these, yes? And so let me just, I need to write something to make sure, I want to make sure you guys are clear on how we find the matrix regular representation of a typical algebra. As good a place as any to do it. So hyperbolic numbers, again, x plus jy, such that x and y are real numbers. So essentially, I'm thinking of this as being R2, with 1, 0 being 1, and 0, 1 being identified as j. So to calculate the matrix of, let's say, x plus jy, well, that is x plus jy, right, times E1, and then x plus jy times E2, just to be obnoxious for a second here. But, you know, E1 and E2 here are just the what and the what, so E1 is 1, right? E2 is j. So that gives us x plus jy. And this gives me, you know, xj plus y. But with this identification, and of course remember that this is also my stupid hidden column notation, right? just to be, I'm always using that. This is nothing more than x, y, y, x. And so that's why the matrix regular representation of a hyperbolic number is exactly just this. Right? Zero divisors, it's, as we worked out last time, a squared equal to b squared. So there's really two pieces, the y equals x and the y equals minus x piece. The reciprocal is really cool. This is 1 over a plus bj, like that. That is, in fact, if we define conjugation, right? Conjugation to be x minus jy. In other words, you know, say that this is z bar is equal to that. Then 1 over z, you can write as z bar over z bar, which is in fact x minus jy over x squared minus y squared.
We never established that the matrix representation is unique.
The matrix, once we choose a basis, it's unique.
Okay.
Yeah. But it's not unique. I mean, it's not unique. If we choose a different basis, we'll get a conjugate representation, yeah. That is true. But here we're working with the standard basis, so it's like, eh. Okay, so this is the reciprocal. Of course, the one case we don't have a reciprocal, I mean, if x squared is equal to y squared, then we're out of luck. That's exactly where the determinant of this is 0, which is just fitting all together, right? But there's more. In fact, the hyperbolic numbers are isomorphic to the direct product of R and R. Now, direct product algebra, what that means is we just do the operation, each component, by the standard rule, whatever it is. Here's the direct product algebra. AB times CD is AC times BD, comma BD. I mean, what could be simpler, right? And you can show that psi of AB equal to that, and psi inverse of that. These are this is an isomorphism. That's the inverse, right? In particular, if you look at just psi inverse of J, like what's J mapped to? That would be x equal to 0 and y equal to 1. So J maps to 1 minus 1. You could also define an isomorphism going from J to minus 1 comma 1. There are sort of two natural isomorphisms, depending on where you send the minus. R cross R can't tell which R came first, right? So there's always going to be some choice of, there's not unique isomorphism, right? I mean, there's more than one way to do it. I think there's just two. But this is an isomorphism. Now, I guess you could ask the question, what's the regular representation of R cross R look like, right? I mean, this is also R2 with a different algebraic structure. What's its regular representation? So we want to look at what's the matrix of A comma B, right? AB times 1, 0, right? AB times 0, 1, right? Which is A comma 0, 0 comma B in the current algebraic structure, which, as you just said, is in fact the diagonal matrix. Yeah, 0, 0, 0, B. This is, of course, a special case of the theorem I told you guys at the end of last class, which is if we have a direct product of two algebras and we look at the regular representation of their direct product, we get a block diagonal direct sum of the representations of the respective algebras here. What's the representation of the real numbers? This 1 by 1 matrices. But anyway, so that algebra is isomorphic to the hyperbolics. Now, this direct product algebra, in many sense, is much easier to think about, right? Like, what are the zero divisors in B? Basically, you got 0, well, A comma 0, and 0 comma B. I mean, the zero divisors are literally the so-called, I mean, x and y axes in that algebra. So one of the things I thought it would be interesting to look at in this paper was the question of the quadratic equation. See, because one of the things we learned in abstract algebra is that if you have isomorphic algebras, they maintain the solution set to equations. I mean, we usually, right? It was one of the theorems. If we have two algebras are isomorphic, if you look at an equation, one algebra, the corresponding equation in the isomorphic algebra has the same number of solutions. And you can say more than that. But think about the quadratic equation here. If I look at the quadratic equation in the hyperbolic numbers, that's kind of terrifying when you actually look at what that means. King can attest to this. He's worked on some of these. When you actually work at it, it's horrible polynomial equations, right? Yeah. A system of polynomial equations, coupled polynomial equations. Quite nasty. Quite a nasty business. But if we take the inverse, psi inverse, and map it to the direct product algebra, this becomes, you know, and then use better notation like this, that, and that. We get this equation in the direct product algebra correspondingly, and just collecting things together, we get x squared plus b1x plus c1 and y squared plus b2y plus c2. And if I give this pair of equations, don't write it as a vector, but just give it as a pair of equations, any high school student could do it. Many high school students could do it. Fine, fair enough, you got me. And if you think about that, well, there's all kinds of cases, right? You could have distinct roots for one, but not the other. You could have distinct roots for both. You could have a complex root for one, but not for the other. You could have a repeated root for one. I mean, there's all kinds of nuances there, but if you, all of those things have to also appear in the hyperbolic quadratic equation. So you have at most 4 distinct solutions to a hyperbolic quadratic equation. Or as few as none. Because it could be that both of the underlying real quadratics are actually irreducible. There could be no real solutions and consequently no corresponding hyperbolic solutions. Does that make sense?
Can you use that for any equation on hyperbolic? Is that isomorphism?
We could use that. We can use that isomorphism to study any hyperbolic function, yes. That's a useful technique, to trade the hyperbolic question for a corresponding problem on the direct product algebra, yeah. We've been successful in using that in various places. Dual numbers. Again, another 2-dimensional algebra, basically based on a nilpotent element, an element which squares to 0 but it's not 0 itself. They have these strictly lower triangular representations in our thinking. You can also look at nth order dual numbers, which is Rn with a nth order nilpotent element, and it has a strictly lower triangular, excuse me, just a lower triangular rather, not strictly, a lower triangular matrix representation. Here's the 3 hyperbolic numbers I talked to you guys about. That is the set, things of the form A, x plus jy plus j squared z, where j cubed is equal to 1. The regular representation looks like so. There is actually an isomorphism between this and the direct product of R and C. That isomorphism is explicitly given in the paper by Nathan Bedell. I'll show you that.
Why do we never look at the dual numbers more? Because most of the calculations have to get into it surprisingly uninteresting.
I don't know if there's a good reason for it. Now Nathan had a big, like, 45-page paper that he had the good sense to split into 3. So we got to figure out which one it is. I think it might be doing algebra. Here we go. There's actually some nice, this is actually worth looking at as you're reading about now, corresponding to my section. He has, there's some nice discussion here. He gets a little abstract in places that, I mean, it's good if you like it. I don't know if it matters too much to us in here, some of his stuff, but it is of, I think it's correct. Anyway, here. So the determinant of this matrix actually works out to that. And this was, Min pointed this out in like the first couple months I was working on this. Min was excited. He's like, look, I found this. I was like, oh, cool. But this is important because if the sum of these is 0, that's a 0 divisor. Or if this thing is 0, it's a 0 divisor. So this is 0 if you put A equals B equals C. So the line in the direction 1, 1, 1 in the 3 hyperbolic space makes that factor be 0. The set of ABC, which makes this 0, well, that's the plane with that direction, with that normal 1, 1, 1. So the 1, 1, 1 and the plane normal to that, they're all 0 divisors in the 3 hyperbolics. And that actually kind of tells you something about how to set up the isomorphism to C cross R, right? Because 0 divisors have to map to 0 divisors. So if you suspect that there's an isomorphism between the 3 hyperbolic numbers, right, and the complex across the reals, or vice versa, well, these things, what are the 0 divisors? They look like this, right? Z0 or 0x. I mean, those are the 0 divisors in the direct product algebra because C and R are both fields, so they have no 0 divisors on their lonesome. The 0 divisors have to come from the complementary 0, like that. That's how they appear. So you see, these kinds of things must map to those kinds of things under the isomorphism. Of course, you could also be a little more, the other way you can look at it is there's got to be some J. There's got to be a J, quote unquote, in the isomorphic copy, right? J is something that's non-zero that cubes to 1. So how do you build that from a pair of real numbers and complex numbers? I think what you got to do is take the third root of unity for your complex component and 1 for the other. You square it, and then you cube it, you're back to 1 again. 1 is 1, 1. In this algebra, the identity is 1, 1. That's how I go about finding isomorphisms, thinking about these thoughts.
I think it's also like rotation.
Rotation?
If you rotate, I mean, like the hyperbolic number, you can rotate.
Yeah, I don't. How do you see rotation?
I mean, you have a line that's perpendicular to the plane, so you rotate it. But it is a plane, so I guess it's related to its complex number more than just.
So you think the plane is the complex numbers?
Yeah.
The plane is the complex numbers, and the normal line is the real numbers. Is your idea?
Yeah.
I like that. I bet it's right.
I mean, if you got like 3 distinct lines that perpendicular to each other, then it will be all 3 rather than times complex number.
But identifying the plane with the complex numbers. Yeah. So here, that might be a geometric description of what this map means. I mean, we did it algebraically, I think, but so basically phi of j is that, and then the inverse would be this. I don't show how to do that, but that's what it is. And yeah. So let's see here. What did I say? Oh, I actually look at the inverse image of 0, comma, complex number. And that maps to, check it out, a plus bj plus cj squared for, what are a, b, and c? A is 2x over 3, b is that, and c is that. And if you add this a, this b, and this c, you get a plus b plus c, which is 0. That a plus b plus c, which is 0, is, what is that? That's the plane, isn't it? That's the plane with normal 1, 1, 1, yeah. I think it's what you said, King.
But I'm not sure how to relate the plane to the maximum.
Oh.
I mean,
Yeah.
you see it as all three, but apparently the hyperbolic number must be isomorphic to
But the geometrically, right? So the plane with 1, 1, 1, right? And then let's try to simultaneously picture the what are we doing? R cross C in my there, right? So that if I'm so foolish as to try to draw both of these pictures at once, which is debatable, X, Y, Z, right? I'm using X, Y, Z for this guy. So really, you might say X, comma, Y plus IZ, okay? Where's the identity in the blue? The identity. This has 1, 1, right? AKA 1, 1, 0, right? So the identity in this is actually where, if I look at it, it's actually like in the XY plane, it's like here-ish, right? And where is J? I think in the blue, J is complicated, right? In the blue, J is the this thing. What that 1, so it's at x equals to 1, right? And where is that for the y and z? 2 pi I over. We were talking about this earlier today. This is how today started. Third root of unity. We were covering the extension to the Q adjoin cube root 3 today in abstract 2. Like we were talking about this earlier. Is it minus 1 plus I root 2 root 3 over 2? Was that it? Is that what I have here though? Yeah. So that's like y is a little bit negative, right? And z is, so like that's kind of up here-ish somewhere, right? This is j in the, that's the image of j. That's not actually j. That's the, I'll put some quotes on it. Now, if I was so foolish as to try to draw the other original algebra and where stuff is there in, say, red, where are those things? Originally, we're looking at H3 as what? R, JR, J squared R, right? So the original thing is that 1 is 1, 0, 0. J is 0, 1, 0. And J squared is 0, 0, 1. That's the hyperbolic. That's the 3 hyperbolic basis. And so there, so J is actually like here, right? And 1, where is 1? Well, 1 is, yeah. So it looks like
Also dilation, because
we're doing some kind of, and it's also a dilation, huh?
yeah, because the vector 1, 0 doesn't have many nodes. So
Ah, right.
yeah, I just think purely rotation, like we rotate 1, 1 into x as the alpha, and then y is the sigma.
Huh.
So I mean, r times 0 and 0 times c is r is 0 divisor of that algebra.
Mm-hmm. Yeah, those are the zero. Yeah.
So I just rotate the line in the plane to corresponding into that r times c.
So you just, yeah. I understood that. What you're saying to start with, it makes sense. I was just trying to, try to be more. What specifically is the rotation? I agree. It's also a dilation, though, right? Just like
I thought he used that, but he used a little bit.
here's another example of that. So the mapping that was that I was looking at a second ago. It's kind of an important point. This map for the hyperbolics. So we have what? We have psi of what is it? A comma B is what? We have, and you see, isn't that neat how the zero divisors appear in the isomorphism like that? That's not an accident. So if we kind of try, this is actually much more manageable, right? See, because if we draw on the same picture, right? If I think of this being, 1, and then this being, let me stop. There's something I'm not saying right. My point, though, was if you look at, for example, what's the length of A comma B? Well, it's the square root of A squared plus B squared, right? We use the usual. I insist on using Euclidean topology for all of these algebras, right? We'll just use the natural. Now, some people would say that's wrong because we're not using the algebraic structure to build the notion of continuity. But I've just found it important to do that because the algebraic structure is married to zero divisors, and zero divisors do not play nicely with ideas like positive definite and just like the things which make a norm, zero divisors are not part of that. So the beautiful fact that you can pick a norm on the complex numbers that's multiplicative, that the fact that that's gone means that directly doing topology with respect to the algebraic structure is, I don't think it's natural, actually. Well, anyway, I guess that's one of those things. If somebody could figure it out more naturally, maybe that would open up other things we don't see. But anyway, that's the length of this. What's the length of the image? So this is just, that's the same as saying the length of, let me just use different notation. What's this vector? This vector is A plus B over 2 and A minus B, if you'll allow me that notation for a second, just to be clear, and I guess to be not so clear, actually. So that's 1/2 square root of A plus B squared plus A minus B squared, right? Which is what? A squared plus 2AB plus B squared plus a squared minus 2ab plus b squared, which is, what is that? These guys are canceling, and we've got ourselves 1 over 2 square root of 2 times a squared plus b squared, aka, the square root of 2 times the length of AB. Oh, I'm sorry. 1 over the square root of 2, right? So this isomorphism is not an isometry. Or, I mean, it does not preserve, it does not transport the notion of vector, it doesn't maintain the length of vectors going from, the direct product to the hyperbolic numbers. In fact, it is a dilation. It dilates by, in fact, it's shrinking by a factor of 1 over root 2. I think this has significance later on. For example, as we study sequences and series, we'll learn, if we were to look at, for example, the sum n equals 0 to infinity, all right, of xy to the n. That's the geometric series in the direct product algebra. Here I mean right? And in fact, that you can just look at as a paraseries. They're decoupled, and each one of them is just plain Jane geometric series. And when does that converge? Need absolute value of x less than 1. Absolute value of y less than 1. So if I was to picture that, right, in the direct product algebra, where does this geometric series converge? Yeah, in a square. That's where I get convergence of both. What would happen if I take this series and map it under the isomorphism to the hyperbolic numbers? What series would that give me? I'm pretty sure if I map this by, what's my current language? Psi, yeah, psi, right? I get the, yeah, well, that's a good question. I should be more careful. What do you think it was to give me? Oh. Yeah, I'd actually have to stop and think about that. Ah, curses. Yeah, I'm not. I was about to make the mad leap that the geometric series should map to the geometric series. But that's a flaw. I haven't proved that. I don't know. I mean, the geometric series in the hyperbolics, the one I'm talking about here, is just this guy. And we proved in the paper I did with Daniel. Let me look it up right quick. Oh, I have these linked on my webpage too. I could just use those. I will eventually find it. Power series. There it is. For any commutative algebra A, the geometric series sum over z dan converges to 1 minus z, 1 over 1 minus z. That's still true for all z and a such that 1 minus z is a unit. And you need that the length of z is less than 1 over ma. So in fact, this is the geometry. I mean, that theorem tells me that this converges for 1 over root the norm of z being less than, what was it? 1 over ma. Now ma, you're like, what's ma? Well, ma is the multiplicative constant. I prove that for any algebra, you can find that there's a constant. If we look at the norm of z times w, I prove that that's less than or equal to some constant, ma, times the norm of z, norm of w. So I don't, this is what replaces that super nice, length of the product of two complex numbers is the product of their lengths. The length of the product of two algebra numbers is not the product of their lengths. It is less than or equal to the product of their lengths times some constant. For the hyperbolic numbers, you can actually work out that this m sub a is minimally taken to be the square root of 2. And so this is actually 1 over the square root of 2. And I can't help but think that that 1 over root 2 has something to do with that 1 over root 2. That's what I think. But I think I may have been, I was giddy. I was hoping I could just say this maps directly to the geometric series. Homework problem. Figure out what this actually maps to, right? It's something I'll let you guys do. I won't try to do right here. All right, let me get back on track here. I have gotten considerably off track. Sorry about that. More examples to show you guys. So dual numbers, triple. Hey, look at this. Here's what happens if you take the direct product of h and h. We had direct product of h and c last time, remember? So we had like a complex block and a hyperbolic block. If you have h and h, you get two hyperbolic blocks. There's the 4 hyperbolic numbers. They look like that. Here's c cross c, the direct product of c and c. Those look like that. There's actually a vast literature on several complex variables. And I'm not an expert, and that worries me. I'd like to know more.
So I'm guessing that you scrolled a little bit. Kind of about how we were talking about.
Which, where, what?
Like the plane and the line.
Where were we talking about?
You said it was isomorphic to up there. Scroll a little bit. Right there. Right at the line of writing above example 4.2a. So I'm guessing if it's isomorphic to like c cross r cross r, we can also do the thing where it's probably going to be a plane of two lines then.
Yeah, but we're in 4 dimensions though, so.
Well, the lines.
Yeah. I mean, it's also the case that it's isomorphic to c cross the hyperbolics, right? Because r cross r is hyperbolics.
Yeah.
But, yeah. There's quaternions. They have the regular representation that looks like that. They're kind of interesting, non-commutative, right? Here's another non-commutative algebra. If you just multiply 2 matrices, that defines an algebra on R4, right? The so-called matrix algebra. And the regular representation of that looks like this. It's kind of like AI, BI, CI, DI. You might recognize that as the tensor product of A, B, C, D, and the